Hello everyone, this is Chandan Jha, and in this video I am going to discuss basic concept of differentiation through understanding tangent lines and instantaneous velocity. So without any delay, let us start one by one. So here, the tangent lines. This is the line that just touches the curve at a given point. Now if we follow German mathematician Leibniz, he has defined tangent as a line that passes through a pair of infinitesimally close points of a curve. A line which will pass through very close points, very close 2 points of a curve. So if we consider this example, fx is equals to 15 minus 2x squared, then the curve will be like this. Now here, if we have to find out the slope of the tangent or the tangent line at x equals to 1, then how can we determine it? Here only one point has been given, x equals to 1. And through one single point, infinite numbers of line are possible to draw. So here you could see this yellow line is also passing through x equals to 1. This green line is also passing through x equals to 1. And here this blue line, that is the tangent, is also passing through x equals to 1. Now the question is how to find out the slope of this tangent where only one point has been given. Now let us have a close look here. Here we could see that green line indicates the second line and the blue line indicates the tangent line. And we know to find out the slope of any line, the formula is y2 minus y1 by x2 minus x1, where y2 is basically f of x2 and y1 is f of x1. So if we apply that formula to find out the slope of the line, then slope of this green line, that is second, is f of 2 minus f of 1 by 2 minus 1. And after calculating this, we shall get slope of the second is equals to minus 6. But we have to determine slope of this blue line, that is tangent. Now here, approximate slope of this green line is minus 6. But we have to find out the slope of this blue line, which is almost minus 4. Then, if we apply this formula of slope, f of x2 minus f of x1 by x2 minus x1, and we form this table here, then we could observe as we are going nearer to point 1 here for 2, 1 at the point 1 has been already given, and we have considered this point 2 through which the second is passing. And here if we consider x equals to 2, then our slope is minus 6 that we have got through our calculation. Now as we are approaching towards 1, the slope is going nearer towards minus 4, which is the exact slope of this tangent line. Similarly, if we start from 0 from here and we are approaching towards 1, then again the slope gets changed to minus 3.9998, that is almost 4. So we could see when the points are nearer to 1, because we have to find out the tangent through x equals to 1. So you could see when we are considering a point nearer to 1, that is 1.0001, then our slope is coming almost minus 4, very nearer to minus 4. And also when from left hand side we are approaching towards 1, then also the slope is very nearer to minus 4. Thus we can conclude here, if this blue line indicates 1 minus delta, where delta is infinitesimally small value, because means difference between 1 minus delta and 1 is very less, that is infinitesimally small. So if this blue line indicate x equals to 1 minus delta, then this point will be f of 1 minus delta. Similarly here, if this right hand side indicates 1 plus delta, then this point will be 1 plus delta. Now if we have where delta tends to 0, now we are going to find out the slope. So slope of the tangent, that is a line passing through a pair of infinitesimally close points, that is if we consider 1 minus lambda and 1, then if we apply the formula f of x2, here f of x2 is f of 1 minus f of x1, that is f of 1 minus delta, by x2 minus x1, that is 1 minus of 1 minus delta, then this will become plus, and this we shall get f of 1 minus f of 1 minus delta by delta. Similarly, if we consider the slope from right hand side, then f of x2 minus f of x1, that is f of 1 plus delta minus f of 1, by x2 minus x1, that is 1 plus delta minus 1. And here we get f of 1 plus delta minus f of 1 by delta, where we have to remember delta tends to 0. Thus, slope of a tangent, we can say f of x plus h minus f of x by x plus h minus x at x equals to 1. If we are considering the tangent at particular point x, then we have to apply this one. Previously x equals to 1, but here we are considering a general case when we have to find out the slope of the tangent. Then we have to apply this formula, f of x plus h minus f of x by x plus h minus x. Or we can also apply f of x minus h by x minus x plus h, where h tends to 0. In previous example, I have considered this h as delta. Here we are finding out a general formula. Now, after combining this, we can write slope of a tangent is limit h tends to 0 f of x plus h minus f of x by h, and also f of x minus h by h. Now, if we consider y is equals to fx, then this total value, this whole thing, limit h tends to 0 of x plus h minus x f of x by h, where these points are very near, x plus h and x are very close, infinitesimally close to each other as h tends to 0. For that, we write, instead of this part, it is a notion, we write d of fx. This indicates a very small change in the function, in the curve. This indicates d of fx, and this h is difference in x. So that is why dx, and that is also h tends to 0. So when the change is very small, we denote it by dx. So d of fx means dy, because y is equals to fx, by dx, and that is nothing but limit h tends to 0 of f of x plus h minus f of x by h, and that can also be denoted as f prime of x. So f prime of x means basically dy by dx, and that is d of fx by dx, which indicates a small change in the curve with respect to small change in the x-axis or in the domain of the curve. Now let us understand one more example, instantaneous velocity. So the velocity of an object under motion at a specific point of time, that is instantaneous velocity. So if we consider a path y is equals to f of t, where t indicates a particular time. Say for 1 second the body will cover f of 1 distance. So if we consider y is equals to f of t as this path, and we have to find out the instantaneous velocity of this body at particular time, at a specific point of time, that is at t is equals to 1, then how can we determine it? Now here what we are doing, we are going to apply the concept of average velocity, and for average velocity we have to find out change in position by change in time. So here again we are considering a very nearer point to t1. So in left hand side we are considering t1 minus h, another point in the left hand side of t1, where h tends to 0. This indicates the point t1 minus h is infinitesimally close to t1, and this point will be f of t1 minus h. Similarly, in the right hand side, if we consider t1 plus h, again this also indicates that t1 plus h is very close to t1, and this point will be f of t1 plus h. Now, to calculate instantaneous velocity, as I discussed, it is calculated similarly as we determine average velocity. That is, but the time interval is infinitesimally small. Time interval is infinitesimally small. The difference between t1 minus h and t1 is very small, and as similar to t1 plus h and t1. They are very close to each other. So that is why it is written here, the time interval is infinitesimally small. Then how can we calculate this instantaneous velocity? Let us see. So instantaneous velocity is equals to average velocity from t1 to t1 plus h, or average velocity from t1 minus h to t1. Now, how to find out average velocity here in this curve? Let us observe. So, average velocity is equals to change in position by change in time. And change in position can be written as f of t1 plus h minus f of t1, because this f of t1 plus h, this function indicates the position. So change in position in small interval. So f of t1 plus h minus f of t1. This is the difference, the very small difference in the position. And change in time is t1 plus h minus t1. Thus ultimately we shall get h. And this can also be written as the change in position from t1 minus h to t1. So this can be written as limit h tends to 0 f of t1 minus f of t1 minus h by difference of t1 and t1 minus h. That will be ultimately h. So here also we could see the change is very small in the function, and the change in the time interval is also very small, that is h tends to 0. So this can also be written as d of ft. This indicates very small change in the path, f of t, very small change in the position, and that will be denoted by d of ft. And this h tends to 0, which is nothing but the change in time interval, and that is also very small, infinitesimally small, that is so small that it is very close to 0. So that is why we are writing it as dt, and that is equals to dy by dt. And we can also write it as f prime of t. So when we have to determine the change in function with respect to infinitesimally small change in its domain, the statements are very important. When we have to determine the change in function with respect to infinitesimally small change in its domain, then we use derivative, and which is defined as limit h tends to 0 f of x plus h minus f of x by h, where this numerator indicates small change in the function, and this denominator, where this numerator indicates small change in the function and its denominator indicates small change, infinitesimally small change in its domain. So this is the change in x plus h and x. The difference is h, and it is h tends to 0, that means infinitesimally small change. And also from left hand side, and notionally we write it as d of fx by dx is equals to dy by dx, and this is the formula for derivative, or you can say definition of derivative, and the concept of derivative will be used for this discussed area. So when we have to find out the change in function with respect to infinitesimally small change in its domain. So that's all in this video. Thank you for watching. Hope it will help you.